Okay, so this is the third part of the training course. Today we'll talk about the code structure for serial code and for the parallel code. And we'll also talk about how to apply self-code, more specifically how to prepare inputs and how to read outputs. Okay. This one? Okay. Ready? All right. Thanks. All right. So we are now on slide number 2. Okay. So this picture shows the flowchart for the serial version. Okay. So the parallel version essentially follows the same structure. Of course, each block will look slightly different. Some blocks actually look very different. Okay. But the flow structure are essentially the same. So you can see there's a big time stepping loop there. Okay, that's the major part of the self code. And outside that, you have some initialization steps. Okay, and for each block, I try to attach a number to it, the percentage CPU spent on that particular block. Of course, those numbers will vary with the applications. So I got those numbers from a recent Cori run. Columbia River Plume run using the serial version 1.5K2, which is very close to the current web version. So you can see that.
Hi, Joseph.
Yes.
I have one question.
Sure.
That's when we profile the program, that we found that this time consuming is related to the grid. Is that right? Related to the grid size and the grid quality.
Yes, I think it definitely depends on the grid size. Yeah, so those, and I say those numbers are not fixed. It really depends on the application. So I show you those numbers to just give you idea, which part are most time consuming as compared to other parts. Okay?
Yeah. Okay. Thank you.
Sure. So the first part of grid is computation of geometries because we are using unstructured grid. You need to compute the collectivity tables. There are lots of them, okay, especially for parallel code. And then after that is done, then you initialize the state variables. The first part of the time stepping step, you're reading all the forcing files for this particular time step. And then you proceed to doing backtracking, which is one of the most time-consuming part of the code. The turbulence closure is, of course, used to compute all the diffusivities, mixing coefficients. It's reasonably cheap. And this preparation part is the assembly of global matrix in finite element methods. It's also one of the expensive part because you have to evaluate lots of integrals. So surprisingly, perhaps, the solver part, the JCG solver part, consumes very little time compared to other parts because the solver is really efficient. It's JCG. I'll talk about the solver later. And then after elevations are solved, then you solve the momentum equations for the horizontal velocity uv. Okay, so and then after that is done, then you solve the 3D continuity equations to get the vertical velocity w using a finite volume method, as we discussed during last lesson. So there are two algorithms to solve the transport equation, UM versus upwind. Actually, the third one is second-order upwind TVD methods. So depending on which algorithm you use, this percentage may vary a lot. So what I show you here is actually the upwind methods, which is one of the cheapest compared to EOM or TVD. So the block after following the transport equation is nothing but the recomputation of new z coordinates based on the newly computed elevations, and also update the wetting and drying flag. So this is a tricky part I have to grapple with when I write the code. The last part is the global output part. Okay, and then the iteration goes on. So next slide, number 3. So I like to give you, I won't go through the code line by line, but the code is well commented, so you should be able to get lots of information from reading the source code. But I like to go through major blocks of the source code. Okay. So the philosophy when I write, when I was writing self-code, I try to follow is that the code should be easily readable by me and by other people. Okay, hopefully, that's certainly my hope. And for that reason, you can notice that I don't use lots of subroutines unless they are absolutely necessary, because my belief is that subroutines really breaks the flow. So you have to jump back and forth. I didn't really like that style. So the main program actually contains most lines here. Of course, in some cases, subroutines are absolutely necessary. They have well-defined functionality. Then you have to use them. So the beginning part, I'm talking about the serial code structure now, is a bunch of declarations of parameters. Okay, so for serial code, we are still using static memory allocations. Okay, this is for a good reason. We actually tried dynamic memory allocation, and that slowed down the code up to 30%. So we think it's not acceptable. So of course, with static memory allocation comes some inconvenience. So if your grid size is too large, so you need to change some grid dimensioning parameters here. And sometimes your compiler, your system's memory may not be large enough, so you need to reduce those parameters. So the symbol of the variables are more or less self-explanatory. So first one, MNP is max number of loads. MNE is max number of elements. MNS is max number of sides, and followed by maximum number of vertical levels. Okay, so those four are most likely to be adjusted by your specific application. And if you use non-zero, if you use some tracers, passive tracers, then you need to adjust these n-tracers. And MNEI is maximum number of labeling elements and nodes around a particular node. Okay. And next two parameters, MNE underscore KR and MNEI underscore KR, are used for kriging. And MNOP specifies maximum number of open boundary segments allowed. And next, MNOND specifies the maximum number of open boundary nodes allowed along each segment. So for the corresponding variables or kind of parameters for the land boundary are specified for in the next two parameters. And this MNBFR is maximum number of forcing or tidal frequencies allowed. Okay, 15 should be plenty. And the next couple of parameters are associated with the JCG solver, so you don't usually need to adjust them. And this particular parameter, MIREC, is really system specific, because in one of our old systems we found that if output size, file size exceeds 4 GB, it somehow cause some problem for our post-processing scripts. So we introduced these parameters to basically warn the users your output size for each stack is too big. Okay, so and then most of the arrays, multi-dimensional arrays in particular, the indices are arranged such that the cache efficiencies are maximized. Okay, so the first index usually correspond to the innermost loop. Okay, so that way to maximize the cache efficiency. So most of part of the code are actually very easy to read. I'll give you an example later. So it's basically looper one user side node or elements. Okay. So let's go through some major blocks. The first block of the code, you read in the vertical grid, the S coordinates and Z coordinates, if you use the Z coordinates. Okay, and then before you can read the horizontal grid, you need to understand, you need to know which coordinate system you are using. So you need to read the couple lines from a parameter file, param.in, because those parameters are specified there. For example, the CPP projection centers. After that, it's long, then you read in the horizontal grid information and the open boundary and land boundary information there. So once you know the horizontal grid, then you proceed to computing the collectivity informations. So on the right, you can see some diagrams which show the convention I follow when I write the code, the local collectivity information. So for given triangular element, the three load 1, 2, 3 are always arranged in counterclockwise fashion. Okay. So and the first load is always opposite to the first side. The second load is opposite to the second side, etc. Okay, that's how you number the local side. Okay, those are local indices. Okay, don't get confused. Don't confuse them with the global index later. Yes.
You do this in the code. There's no requirement that grid files adhere to this. Is that true?
For the side information, yeah, that's computed inside the code. You don't have to worry about that. Yeah, you only specify load and specify the element collectivity information. Yeah, but the element, the collectivity information for each element must be such that the three local loads must be arranged in counterclockwise fashion. Otherwise, the code crash will tell you this particular element has a negative error. That's what happened. Okay. So the next picture shows the ball overload surrounding elements and the surrounding loads of particular given load J. Again, everything is arranged in counterclockwise fashion. Okay, that simplifies a lot. Some computations of some integrations of file elements. Given a particular element, it has up to 3 labeling elements, right? The number here. And again, the numbering of labeling elements follow the side. Okay, so the first labeling element is always opposite to the first load, etc. And yes?
How do you, where do you start when you're looking at the elements surrounding J? Are those kind of clockwise? How do you determine?
It's somehow somewhat arbitrary, you know. But if this load happen to be situated on the boundary, then it's no longer arbitrary. Think, right? It's an open ball instead of a closed ball. Closed ball, yeah, you can start from anywhere you want. But if it's an open ball, then you need to start particular load in order to be counterclockwise. So given a particular side here, shown here as a red dot, you can have up to 2 adjacent elements, 1 and 2, and the order of those 2 elements is always such that the first element, the global index, element index of the first element is smaller. Okay. So that's a convention we follow. So with that, you can easily construct a local coordinate system, which in many cases become very convenient. So x direction is normal from element 1 to element 2, and y is 90 degree from the x. So next slide. If you use a Shapiro filter, okay, you also need to compute the side neighborhood information. Here, each particular side is inside a quad formed by 4 neighboring sides, and if it's not, then you need to extend the stencils for internal sides. Okay, so this kind of information is pre-computed, so you don't have to compute this every time step. Okay, and that's the end of the collectivity information. Well, actually, there's another one, the kriging. Okay, so for the parallel code, actually I move this kriging part immediately after the side neighborhood information part. So it's because they all belong to the collectivity information. So for kriging, given a particular element, then you need to construct the kriging cloud. In serial code, you can construct the multi-layer, multi-tier kriging cloud, whereas in parallel code, for efficiency, we only allow 2-tier. And once you create the kriging cloud, then you need to assemble the kriging matrix, which is a geometric quantity, and then you need to invert that, save it, and use it again and again during the time iteration process. So after all this done, then you read the rest of the parameters in param.in. And then the initialization stages depends on whether or not you are using hot start or cold start. Okay, but the end goal is the same. Basically, you initialize give the initial values to all the state variables: elevation, 3D velocity, salinity, temperature, density, etc. So the cold start essentially, you first of all need to initialize the bottom indices associated with each load, because those are needed when you reading the initial condition for salinity and temperature. And of course, you need to initialize the wind field and lodging field if you use lodging, and if you use a Galton turbulence closure library, then you need to initialize that library as well. For hot start, you basically read all state variables from one file, hotstar.in. Okay, so and also in addition to that, you also need to find the position to read from, starting position to read from in all those time history files. So after all state variables are initialized, then the code will write the initial header portion of the global outputs, and you compute the initial z coordinates and initial wetting and drying flags. And if you use bed deformation module inside, then you'll compute the bed deformation information as well. And then, as we discussed in the previous lecture, you need to convert the side velocity to load velocity in order to do backtracking. So that's done here, initial velocity and loads. And then you need to compute the initial density based on the initial salinity and temperature using equation of state. And if you use a heat or salt exchange model, then you need to initialize that as well. Okay. So the time stepping part consists of following blocks. And as I said before, the structures of those blocks are pretty much similar to each other. On the lower right corner, you can see a typical loop. In this particular case, it's loop around all sides. Okay, so first of all, you want to check if the side is dry or not. If it's dry, then you do some special treatment. Okay, like in this particular case, we just assign 0 velocity to all the initial to the dry sides. Then you do another set of operations for all the wet sides. So This is a major part. Okay. And inside this, of course, in many cases, you need to loop around each levels. It's 3D. So very briefly, so the time stepping part consists of those major blocks. First, if you use a better deformation module, then you compute the current displacement of a bottom from the initial bottom. And they compute the bottom drag, basically CD times the magnitude of bottom velocity. So that's needed in the by the element matrix. So you need to update that quantity based on the newly computed most recent bottom velocity. And if you use a horizontal viscosity, that's computed here, pre-computed, so you don't have to compute it inside this momentum equation. And if you use tidal potential, then those are computed here. And you read in the most recent information from the time history file, like wind stress and atmospheric flux. If you use login for ST, then you compute the current login values. And then read in all the time history files. And in particular, for velocity boundary condition, the values you read in the discharges. So you need to convert that discharge information into the U and V component based on the cross-sectional area of the boundary. But if you use UV3D.th, then the values inside this file are already UV, so you don't need to convert that. And this part is a bit is no longer there inside the parallel code because we're using a different algorithm to compute the baroclinicity. And the turbulence closure schemes, the equations are solved at loads and whole levels. And then you proceed to assembly of global matrices. Okay, and compute those quantities I1 to I5, as we discussed before, and impose the essential boundary conditions and invoke the JCG solver to solve the elevations. For momentum equations, all the UV are solved at side centers and whole levels. So one thing to notice is that if you use Z layers, okay, so you have a staircase bottom as shown in this picture on the top of slide 5. Then you need to zero out this part, the velocity here. Okay, so that's for better volume conservation. And of course, if you use a Shapiro filter, if you use a Shapiro filter, that's applied right after the initial the momentum equation. And the vertical velocity relatively straightforward to solve. They are solved at element centers. And the transport equations, there are two algorithms, just three. But upwind and TVD using all the same routine called do transport underscore TVD. Okay, so for convenience, it's because the lots of steps are similar to each other. But if you use an ELM method to solve for the transport equation, then the equations are solved at both loads and side centers. So in this case, you do need the backtracked values, okay, and the first order characteristic line. If you use an upwind or TVD method, the S and T are solved at present centers. In this case, you do not need the backtracked value for S and T. So this subroutine does all the heavy lifting of solving S and T and present centers, and after that is done, then you we basically convert the SNT and present centers to loads and whole levels, mainly for output, but also for turbulence closure equations. You do need the densities and loads there. If you use the passive tracer modules, then tracer equations are solved in the, again, using this do transport underscore TVD subroutine. Okay, and then you impose the boundary conditions for S and T, and if you do larging, then you need to, that's down here. And then after that, transport equations are solved, then you compute the new Z coordinates and the new weighting and drawing flag. I will talk about this part in detail later. And of course, you need to convert the side velocity back to load velocity for legs backtracking and calculate the new density. Okay, and if you want to do some conservation checks, then you can turn on a particular flag inside param.in. So this part is optional. And last part of the code is to do the global outputs, including the hard start information. So slide number 6. Next couple of slides we'll talk about the some specific subroutines. Okay, the first subroutine, level 0, is used to compute Z coordinates and nodes, sides, elements, and also compute the weighting and drawing flags. So, as I mentioned in the last lesson, we try to follow some rules, for consistency throughout the code, okay, for weighting and drawing. So the rules we finally decided on is that we do not allow partial weighting and drawing within each element. Okay, so element is wet, then all 3 loads must be wet, all 3 sides must be wet. Okay. So the reverse is obviously not true. If an element is dry, it can still have wet loads or sides, right? So the rule for wet for the loads and sides are shown here. The load is wet if and only if at least one surrounding element is wet. Okay, same for the side. If and only if one of the surrounding elements is wet. So for a dry load, then all the surrounding elements will be dry, right? So then you need to enforce some consistency here, because if you first apply this rule, element is wet if all loads are wet, then you end up with some kind of a bunch of isolated wet points. Okay, so you need to weed out those fake wet points. So this consistency rule is strictly enforced throughout the code. So if you happen to add some modules to the code and the code crashes, chances are that you are violating this consistency rule. Okay. So another part of weighting and drawing is that if a load or side becomes newly wetted, that means its previous time step is dry, and then in this current time step it becomes wet, then you need to initialize the state variables there, okay, based on some kind of average. Now we are on slide number 7. So the next subroutine levels 1 is very, yes.
Yep. I have one question about the slide 6.
Sure.
That a side is wet if and only if at least one adjacent element is wet.
Mm-hmm.
And this statement is to adjust, to verify during the every time step, or?
Yes, it's enforced during every time steps. Does that answer your question? Every time step you need to enforce this rule.
Okay.
Okay, so the subroutine levels 1 is very much similar to levels 0, except it has beginning of this routine, you have iterative part that calculate the shoreline. Okay, so as we discussed before, this algorithm typically gives you the better accuracy near the wetting and dry interface, provided that your grid resolution is fine enough. So again, the iteration to find the interfacial load, the shoreline, is basically to go through all loads on the shoreline and then apply the rules I just mentioned to make the elements wet or dry. Okay, if it's wet, then you need to extrapolate the velocity into the wet zone. If it's dry, you don't have to do anything there. So you enforce the consistency rules throughout this iteration. So that's why it's a little bit more expensive. And after this iteration, after you find the final shoreline at this current time step, then you need to do constant extrapolation of elevation and the newest shoreline, as we discussed before too. And in addition to that, you also need to weed out the isolated wet loads, and also set the dry side velocity to be 0 for obvious reasons. And for another thing we found we were working with these subroutines, that if a load is initially wet, that means it's below a mean sea level, and then becomes dry, then you need to somehow regulate the elevation there when it becomes dry. Otherwise, next time, couple of time steps down the road, it becomes re-wetted. If the elevation there is it's pretty bad, it's pretty outrageous, then you kick out lots of noise. So what we did finally there is that for all those nodes, initially wet nodes, we add a very thin layer there. Okay, they are still dry, but the elevations are regulated in this way. So rest of part follow exactly the levels 0. Okay. Okay, now we are looking at the one of the major blocks of the self-code, the backtracking part. It's slide number 8. Okay. So the backtracking part, the major part of the backtracking is basically a loop around sub-time steps. Okay, and within each sub-time step, you are given a starting point. Your task is to find the ending points and ending triangles and levels. So this is done in a subroutine called quick search. So the inputs to quick search is basically starting position and starting triangles, and the outputs include the destination point and the triangles and other things. And one of the major output from this quick search routine is this flag, basically indicating some kind of abnormal cases, which I will explain later. Explain right now. So for the quick search algorithm, this picture basically shows the essence of a quick search. Your main task is to walk from element to element and find the intersecting sides. Okay, so intersecting sides are shown here in this cyan squares. Okay, so given an initial point, okay, and the initial element and the initial velocity, so this black point is the estimated destination point for this specific sub-time step. Okay. But obviously it's wrong, right? Because it crosses an island. So the quick search will correct that when it hits the horizontal boundary. What it does is you will zero out the normal velocity and let it slide. And do the same thing when it hits the wetting and drying boundary. You slide around that interface, And so xt, yt here, the blue dot is the correct ending point, okay, destination point. So, of course, one of the most perplexing problems for this part of the code is many underflow problems. So think about the extreme case, the characteristic line can align perfectly with a particular site. So in that case, you have infinite many intersection points. So to get around this problem, so finally we decided to basically add a random, very small random noise to the starting point. Okay, so that somehow seemed to solve the underflow problem. So there are a couple of abnormal cases. One is that when the characteristic line hits the horizontal boundary or the wet and dry interface, and the tangential velocity there becomes very small, then in that case, there's a later point to continue the backtracking. Right? So in that case, you basically return the current position and the current element, exit the backtracking. Another case is doing some tricky cases, and such as eddy. The iteration can go on and on. Even with more sophisticated tracking algorithm like a fifth order round Jakarta. In that case, we just simply exit. Okay, if the iteration exceeds, I think currently I said 100 or 500 iterations, just simply exit. So as you can see, this quick search algorithm, the logic is a bit complex, but compared to the old algorithm, we found that it's actually very efficient. Okay, the coding becomes very tricky, but it's efficient, and it's essentially a moving target search. Okay, it's not fixed target. So in this case, that's why it's important to keep a clock running, to keep track of how much time left. Yes?
I have a question here. When you do your backtracking, all the tests that you do to see if it's inside NML and then so forth, all the are done with if statement. Is that correct?
Done with what statement?
If statement.
If, yeah.
If statements are very costly. So do you think that the backtracking is spending a lot of time because of all those if statements?
I'm not sure what you mean. I mean, I'm not even sure what's the...
You cannot parallelize if statement. It's not going to be very efficient computational-wise. It's not very efficient. Any if statement really destroyed any parallelization of your code. So that code is very costly, and you spend a lot of time, as you showed the first slide, in the backtracking. So my question is, all those if statements in the backtracking, either the one makes the backtracking expensive?
I don't think so. I don't think the most time-consuming part is the iteration. Walking from the side to side, element to element. Yeah, there are lots of computations. Yeah. But for your question, if statement destroys the parallelization, I don't say that. Because this if statement is still computation, it's not communication. Right?
But an if statement is very costly on a computer.
Well, it's not as costly as when you evaluate, say, a high-order polynomial.
It's more costly than an iteration, for instance.
More costly than any iterations?
But if you have a do loop, it's less costly than an if statement.
Right, but I don't know how. What's the alternative really? Are you suggesting any alternatives there?
No, I was just wondering if the backtracking is costly because of the if statement and if there are other ways of doing it.
Right. We probably should talk offline. You know, I like to
Yeah.
get your idea. Yeah.
Sure.
Right. Thanks. So there are two ways to do backtracking. The first one is simple Euler backward differencing scheme. So this the Euler scheme basically consists of this major loop. You know, you basically loop around each sub time steps, and the inputs to this routine include the starting position, starting element, and how you want to do backtracking, of course, and output will include the final destination point, elements, etc., and also the interpolated salinity and temperature and foot over characteristic line. So it's first order and also, but one thing we implemented in this Euler scheme is that you somehow more or less automatically compute the number of subdivisions, okay, based on the local gradient, the flow gradient. And within each subtime step, so it uses this quick search subroutine to find the ending points. And if you use if you use this linear shape function to construct the load velocity, then you have some additional handles here. You can basically blend the continuous and discontinuous velocities and loads. Okay. And when you do 3D interpolation, you can also do it along a Z plane or along a S plane. And if this abnormal flank NFL is hit, then the time iteration stops. So after backtracking is done, optionally you can do higher order kriging and the foot over characteristic line for U and V component. Okay, and before that, of course, you need to make sure all the kriging points are on the same Z plane, so you need to do some kind of interpolation. And the interpolation of S and T and the foot over characteristic line is done using two alternative methods. The first one is split linear. Basically, you do linear interpolation in one of the four sub-triangles. Okay, so in order to cut down the numerical diffusion. And in this case, you still need to do the vertical interpolation. The vertical interpolation is done using a cubic spline. And the second method is to use the quadratic shape function in the horizontal and the vertical. Okay, so it's a 3D quadratic shape function. And in this case, in the normal case, because the quadratic shape function will involve two layers. Okay, so you need to have you have the choice of which two layers you use. So the way we choose these two layers is to basically find the upwind layer. So suppose the vertical velocity is positive here, then you use these two layers. If it's negative here, then you use these two layers. Okay. And of course, if the foot over characteristic line is close to the surface or bottom, you don't have this luxury. Okay, then you need to use the low flux, the boundary condition to help you together with the shape function. So of course, the higher order interpolation will introduce a numerical dispersion. So the way to get rid of those numerical dispersions is to typically people apply some kind of a filter, okay, mass conservative filters. We tried that, but later on we realized that the mass conservation is not guaranteed anyway in EOM. So why bother? So we just use a simple way, basically imposing the bounds from the labor or the labors. So slide number 10. So the fifth order adaptive Ranjikata scheme is slightly more complex. If you read the code, it's based on the fourth order Ranjikata method shown here. The equations for the fourth order Ranjikatas are here. So you basically split each step into 4 subtime steps, and the final result will be weighted average of all here, okay, XL. And fifth order adaptive Ranjikata basically adds additional adaptivity step. And adaptivity is based on this error estimator delta, which is weighted average of the final results. And then the desired subtime step for the next iteration is calculated here based on the truncation error analysis. Gamma here is just a simple safety factor. We usually take gamma to be 0.98. So the ratio between the delta zero is basically specified tolerance, okay, and delta is the estimated error. So the ratio of these two will determine the next backtracking step. And for efficiency in the code, we restrict the adaptivity loop to be 5 iterations. We don't want to go on and on. And in this case, there's no abnormal flags in a quick search, because if the abnormal case is encountered, then the code will actually reduce the time step. So hopefully we'll avoid hitting the boundary, But if it still hits the boundary and still, after 5 iterations and the tangential velocity is very small, then we'll simply exit. So after the photo characteristic is found, then you proceed with same way as the Eulerian scheme. So in terms of efficiency, the fifth order Ranjikata has a lot more calculations. Of course, it's more expensive than Euler, but the advantages of this method is that you can use a very large time step. Okay, the adaptivities there really enable you to do very large time step as compared to the Euler scheme. And of course, it's definitely more accuracy. We did lots of benchmark tests. Where, for example, the rotating Gauss scale, you can definitely say that the accuracy of the photo characteristic line is dramatically improved. Okay, because of that, the mass conservation actually is also better. Okay, so next slide, you don't see the slide number, slide 11. Okay, well now we'll look at the structure of the parallel code. So the first step of a parallel code is basically to do the domain decomposition. Okay, given a domain, the code will subdivide this domain to many subdomains, and each process will own a particular subdomain. Okay, process 0 will own this. So each subdomains are colored in different colors in this diagram. Okay, and then one thing you need to notice is that the particular subdomain owned by a particular process may not even be contiguous. So on the lower right hand corner, you can see that this particular process owns these two discontiguous subdomains. Okay, so they need not be contiguous. So each subdomain, you take a particular subdomain like number 3. So this original light blue domain is called a resident domain. Okay, and on top of the resident domain, we also augment along the boundary of this particular subdomain one layer of ghosts. Okay, those are hashed regions here. So you can see that the ghosts actually belong to other subdomain. But the resident plus ghost are called augmented domain. Okay. So inside the ghost region, That's where the communication happens. Okay. So as far as each process is concerned, it has its own set of resident node side elements. It has their own local numbering, local indices. Okay. Of course, all nodes and elements sides have their global indices. Okay. That's why there are lots of mapping arrays between local and global, global to local. And between local to local, there's no mapping index, so you have to do communication. So the way Self does the domain decomposition is through this Parmetes library. Okay, so it's actually achieved in two sub-steps. The first step is just to do some kind of very naive decomposition. So, for example, given a total number of elements, you just equally divide them into a number of processes and assign each segment to each process. Of course, this is a very horrible way because the unstructured grid and the numbering can be arbitrary. So the subdomains become very discontinuous. So, but based on this step, you can compute the collectivity information of each process and then invoke this Parmetes library to do the final partitioning. So Parmetes library, very briefly, is MPI-based parallel library and implements a variety of algorithms for partitioning and repartitioning of unstructured grid graph. It's basically a graph partitioning tool. And they are based on the multi-level partitioning and field reducing ordering algorithms and improved upon the older version called Metis. And one good thing about this library is that it minimizes the edge cuts, so it minimizes the disjoint of each subdomain. And also it allows user to tune some parameters for optimal partitioning. So we haven't really done this part. Obviously, this part has implications for the performance. Okay. So this final partitioning is achieved through this subroutine acquire edge grid, and the argument is true. That means the second partitioning, the first partition is false, which is based on some naive ordering of elements. So the next slide, number 12. As I said before, each process will own its own list of variables and indices. There are a number of mappings from the global, local, local to global. Okay, so particularly problematic is the global to local mapping. Okay, because given a global load, it can be owned by many processes, right? So it's not unique. So you need to have this kind of a linked list. Okay, within each entry of the list, you have the information such as previous list, previous entry and next entry, and local indexes, global indices, etc. Okay, so for example, the IEGL, that's the element list, global from global to local. And next basically means the percentage lex means point to next entry, and next entry, and so on. So one thing you need to be careful when you read the parallel code is that you are always looking at the code from each process viewpoint. Okay. And when you do communication, you need to extract yourself out and look at it from global viewpoint. You look at a bunch of processes. So that's something I found very useful. So within each process, this IEGL, the first entry is always the local one, if the element is actually resident or ghost within this process. So the first entry always points to the local element. Okay, so that's for obviously for convenience reason. And anything after that, you have a bunch of processes on this element. So they are ordered according to the rank of the process. Okay, each process has a rank, 0, 1, 2, 3, right? It's in ascending order. So the other two linked lists associated with the nodes and sites, IPGL and ISGL. So in this case, there are some additional issues you need to take notice of. Okay. Because a particular element can only be resident on one process, right? It can be ghost in many processes, but can only be resident in one process. But this is not true for the nodes and sites. They can be situated right on the interface between the processes. So owned by many, they are resident in many processes. And then if you recall, the elevations itself are defined as nodes. So this actually caused some very tricky problems when I was debugging the code. So basically, the computations usually are done within a resident domain. So the elevations and within each resident within each process, by right, it should be exactly the same on the interface, right? They should be exactly the same, but they're not because of the machine precision in each node may be slightly different. And this is a lot of problem until the waiting and dry index got violated, the consistency got violated, the code just crashes. It took me quite a while to debug this. So this is something you need to be care of. So finally, what I did is for this loads and sites, during the communication stage, I basically use brute force and enforce the consistencies according to the smallest rank process. Okay, so the rest of all the elevations, for example, in each process will be carbon copy of the elevations at this the smallest rank. Okay, so the way we do communication, of course, communication is an expensive part. You want to minimize that. So the way we do communication is through the standard MPI protocol. And in addition to that, we also try to bundle up as much as possible. Basically, stack a number of arrays as much as possible before you send and receive them. So this is for efficiency. So this table shows you the typical conventions I follow in the parallel code. Underscore global obviously means this quantity is global. And for the local residents, then the symbols are exactly the same as the serial code. Okay, you don't have anything special there. For ghosts, you add a G there. And for augmented, you add A at the end. So another thing to note is that for simplicity, all the boundary information arrays are not partitioned in the server code. Those are the one-dimensional quantities, so they don't consume a lot of memory. So for simplicity, I didn't partition the global boundary into local segments. So here are some segments in the parallel code that does the communication. Okay, we are now on slide number 13. So before communication, of course, you need to bundle up. The way to do bundle up is to use some kind of secondary data type. So MPI allows you to do that. But even before that, of course, you need to find compute the local collectivity information for each process. Okay, each process is bordered by a number of processes, right? So you need to compute that collectivity information. That's what the upper box is about. So then you create some kind of secondary data types using this MPI type indexed. Okay, The first argument is basically tells the code tells the code how many blocks to be expected. Those are discontiguous blocks. The second one is block length, and the third argument is basically starting address of that particular discontiguous block. And the next argument will tell the compiler what kind of data type it is. Is integer, float, or structure. In this case, it's actually structure. Okay. And then this will be the file data type name. You commit it, you get a data type. So basically the compiler will know how to grab these contiguous blocks from each array. Okay, assemble them into a bigger array. And the first step is to actually send the informations. Okay, you send first before you receive. That's kind of counterintuitive, but for a given process, okay, you are looking at this from a specific particular process. It knows how many ghost elements, ghost loads, or ghost sites it has, right? So you need to send that information to all its neighbors. Then the neighbor will basically receive all those informations and process the information to know how many nodes to send to this particular process, how many nodes to send to another process. Okay, you always send before you receive. And this is done through this non-block send and non-block receive. Okay. So the order is actually not important. Okay. In this case, it's kind of weird. You put a receive before the send. If you haven't sent, how can you receive? But the order is actually not, because it's a non-block. Okay, and also the MPI automatically blocks this receive command until somebody actually sends you. Okay. Next slide. 14. So now you can do this kind of after you send the information, how many loads, how many elements, how many sites you expect, and each process will know how many loads, sites, elements to send to each process. Then, you can, for each process, you construct another secondary data type. Okay. To basically prepare for sending. Okay. You know how many requests from your neighbors, and then you construct this big arrays, for each process. This is what this block is about. And the last part is actual sending and receiving through non-block communication. Okay, so you use this a data type you created for sending and for receiving. Okay, and of course after that, you need to have because you are using non-block send and non-block receive, then you need to wait until all the communication completes. Okay, that's MPI wait all, which is not shown here. So one of the most tricky part of the parallel code is, of course, the backtracking. Backtracking is very nasty in a parallelization sense, because the characteristic line can traverse as many processes as possible. So you can easily get out of the labeling process, right? You can go to label or labels or labels or labels, so anywhere. So for this reason, you need to have a loop. Okay, so this subroutine inter btrack consists of 3 loops. Okay, outer loop, inner loop, and all-rank communication loop. Strictly speaking, the inner loop is not really needed. It's there mostly for efficiency purpose. Okay, what this inner loop does is that as soon as a particular process receives any request from another process, it doesn't wait. Immediately execute the backtracking within its own augmented domain. Okay, that's where efficiency comes from. So this piece of code actually was written originally by Tim Campbell of NRL. I think it's a piece of art, really. It's very, very pretty. So beginning, you basically before you do subdomain backtracking, you do the same thing as the serial code. Hopefully the photo characteristic line will be inside the current augmented domain. Okay, if not, then you basically put the request into a list called BT list. MBT is basically total number of requests. Total number of characteristic lines that exceed the current augmented domain. Okay, so because of that, the subroutine quick search now has some new abnormal cases, basically exit current augmented domain. Okay, so now if you have each process will have its own wish list, okay, BT list, and total number of trajectories. So you will basically construct this BT send queue list, okay, based on the collectivity information. You just similar to what I just showed you there. You will, for each process, it will basically construct a secondary data type and tell other processes how many trajectories I want from you. Okay, and from that, each process will receive the receive requests, okay, and receive data type. And as soon as this is done, you start all-bank communication. But in this case, instead of MPI wait all, we use this MPI wait some. Okay, so as soon as a particular process receives a request from any other process, you immediately execute the btrack subroutine inside its own augmented domain. And if the photo characteristic line is inside this particular augmented domain, you put it into a list called BT done. If it's not, then you put it into a temporary queue, BT queue, and then go back. Reconstruct the BT send queue and iterate until all the requests are handled. Okay. After all requests are handled, each process will sit on some information that it does not really need. Okay. So the photo characteristic line, it's maybe situated inside a process that is different from the originating process, right? So you need to find a way to communicate those information back to the originating process. And this is done through the all-rank communication loop. So the all-rank communication loop is another tricky part. I have to spend some time debugging. But essentially, you do the same thing. You construct a send and receive queue, and then basically to involve the all-rank communication. Process will send and receive, simultaneously. And the final list is called the updated BT list. Okay. Any questions so far? I know this is a bit probably over your head, but just in case you want to add something to the, sorry?
Yes, Joseph, I have a question in your slide 14.
Yep.
You have an update of an NBRQ, and you said an NRBRQ is the number of active neighbors. Where do you use it?
Where do you use it?
Yeah, where do you use it?
I think it's a number 13. Number 13, slide number 13. When you create those secondary data type, you can see that second argument. The loop is around all the labels NNBR.
I was on number 14.
Yeah, in number 14.
The NNBRQ is used in number 14.
Yeah, NNBR is computed in slide 13. Okay.
Yeah, but inside slide 14 you have an MBRQ.
MBRQ.
Great.
Um, oh, okay. That's for the receiving. Because receiving there's a difference between the number of labels when you receive and when you send, right? Those are different quantities. Yeah. Does that make sense?
Well, no, my answer, I don't think you answered my question. In the line where you, first you have the number of active neighbors equal to 0.
Right.
And you have a do loop that you upgraded number of active numbers. You say it's +1, +1, +1. And then where do you use it after that?
Oh, NMB got Q, okay. I know what you mean now. Actually, I didn't show here. NMB got Q is used later for some kind of a consistency check. Yeah. It must match a certain number. Yeah, for consistency check, it's kind of debugging tool. Yeah. If you read this part, it's in inter btrack subroutine. Yeah.
Okay.
Yeah.
But it's not used per se for the calculation of the neighbor and the backtracking.
Not really. No.
Okay.
Right.
Thanks.
Yeah. Thank you. Okay. Before we go to the application itself, I just like to finish this slide. Okay. So I don't know how relevant it is, but this is just another example of you need to be careful when you do communication. This is a JCG solver, and in the box, this is basically algorithm of JCG. Given a linear system, you compute the residual based on initial guess, and you, of course, normalize the diagonal through this Jacobian preconditioner, and normalize they initialize the gradient and go through this loop. Okay, so this loop is exited if the L2 norm of the residual is small enough. Okay, so the arrows here means that you need Gauss exchange, and these circles here means that you need to do global sum. Okay, so because again, elevations are defined as nodes, and nodes, especially also interfacial nodes, can be owned by many processes. So one thing you need to be careful is that when you do this kind of summation, you need to get out of those, so what I call halo nodes. Okay, because you only sum it once, basically, using the value from the smallest rag that owns it. Okay, that's the trick there. Okay, so I suggest we take a break before we go to the next part.